Hello, ladies and gentlemen. Root Beer here with question number 25 on the 2004 Cayley contest. This is the very last question. It's the last one in part 5, or not part 5, part C, and it's worth 8 marks, so it should be the hardest question in theory. Sometimes I think it's a toss-up between 24 and 25, but that's down to personal preference. Usually when they make up the contest, they try and make 25 the one that they think is harder. But everyone has their own style. Anyway, that's enough rambling. Let's take a look here. Question 25. The number of positive integers x with x less than or equal to 60, such that each of the rational expressions 7x plus 1 over 2, 7x plus 2 over 3, 7x plus 3 over... Okay, so we're adding a number and then dividing by one bigger than that number, all the way up to 7x plus 300 over 301, such the rational expressions, these guys, are in lowest terms. Numerator and denominator have no common factors. Okay. So when I read this, I'm thinking a couple things. Jump into my head. One, why did we stop at 300? Okay, I could understand it being an arbitrary number. You know, that's fine. But maybe there's a reason we stop at 300. Maybe if you do 7x plus 301 over 302, that somehow always fails or something like that. If it was 2004, like if we were doing 7x plus 2003 over 2004, I wouldn't question it. Okay, it would just be, you know, it's a gimmick and they just happen to be using the year. Sometimes the year is special, like if it happens to uniquely be a sum of two squares. I've seen that happen before. But usually if it's just they work in the number there just to be fun. Just like in question 24, they had the triangle area was less than 2004. And that was largely meaningless. It was just, you know, it's the 2004 contest. But the fact that we stop at 300 makes me wonder, is there a reason for that? Is 301 a special number when you divide it by 7? Like, why do we have 7x there? Why not 5x or something? These are just the things that pop into my head. Anyway, it might have nothing to do with anything. Another thing that pops in my head, if we're trying to get things in lowest terms, I'm starting to think prime numbers. Okay, the reason being, if the numerator and denominator have a common factor, they'll definitely have a prime number in common. And now that I'm saying that, I'm thinking maybe I only need to check the things with 2 in the denominator and 3 and 5. Like I don't even need to bother with 4. That's something I'm thinking. I don't know if it's true. Just a gut reaction. Now I'm thinking maybe 301 is prime. And maybe they just stopped at a really big prime. But maybe there's some reason to believe, yeah, because if 7x plus 3, yeah, actually I'll write some of this down. So for example, if 7x plus 3 over 4 is not in lowest terms, then either 2 divides 7x plus 3, or 4 divides 7x plus 3, in which case then, yeah, 2 divides it as well. Because that one implies, I mean, if 4 divides something, then 2 definitely divides something. But if that's the case, I can subtract off 2. You know, both of these guys imply that 2 divides 7x plus 1, in which case 7x plus 1 over 2 is not in lowest terms. So yeah, I'm definitely thinking primes. Another thing I'm thinking of, that just popped in my head now, you can't really show a number is in lowest terms very easily. The best thing that you can do is show that some number is not in lowest terms. You know, rule out these x's that happen to have this remainder when you divide by 7 or something like that. That shows that these guys somehow come together. So it's easier to rule out numbers rather than to be able to say, yep, that x, that x, that x, and that x are the ones that work. It'll more be something like these x's don't work, and that leaves this x, this x, this x. So that sort of gives us maybe a little bit of a plan of attack. I don't know. So I think I'm going to stick with these primes here, this prime stuff. So I'm going to say something like, suppose I'm going to write, this is going to be very general statement, and you don't obviously need to write this stuff out if you're doing a multiple choice contest. But I like to write sometimes as though I'm doing a written contest. So I'm going to say something like, suppose 7x plus n over n plus 1 is not in lowest terms. Well, then there's got to be some factor I can find some d that divides n, that divides n plus 1, so that d divides 7x plus n 2. And I can more specifically say, and if I didn't already, I can say d. We can find a prime p that divides d. You can always take out a prime. So p divides 7x plus n. Okay. But then, so p divides n plus 1. So for some k, pk is equal to n plus 1. And then what I can do is I can say, well, I didn't want to say this, but this might be useful too. (7x minus 1). And actually, this had nothing to do with the n that we started with, or the p we chose. What I wanted to do was say that you can get, you need k minus 1. I can also do 7x plus n minus p k minus 1. And that'll get you p divides 7x. Without too much work, you'll get p minus 1. So then 7x plus p minus 1 all over p is not in lowest terms. And so that's what we were going to have, although we've sort of stumbled across 7x minus 1, and I'm liking that just because I think we can actually sort of transform all of these into, if this is in lowest terms, then this has got to be in lowest terms, and backwards. If 7x minus 1 over 2 is in lowest terms, then 7x plus 1 over 2 is in lowest terms. I think 7x plus n over n plus 1 is in lowest terms if and only if 7x plus n minus n plus 1 over n plus 1, which is just 7x minus 1 over n plus 1, is in lowest terms. Is that necessarily true? Well, if I had a d that divided, I could get a p that would divide it, a p that would divide 7x plus n, but then that p would also have to divide 7x minus 1. And if such a p divided 7x minus 1, and if that p was also a factor of n plus 1, then p would have to divide 7x plus n. So yeah, this does work. Okay, so actually, I was just going to make an argument based on primes. I guess I still can, but we just need to find the x's less than or equal to 60. It was less than or equal to, right? Yeah, less than or equal. So that 7x minus 1 is not, I was going to say is not divisible by, but, and that would still be a true statement, but has no factors in common with any of these numbers, 2, 3, 4, all the way up to 301. Now, we don't have to deal with, as I've sort of also already stated, we don't have to deal with 4 or 6, because if 7x minus 1 has a factor in common with 6, it's going to have to be one of the prime factors, 2 or 3. So we just need to check primes, and I think this might make things a little quicker for us. So, really, we just need to check primes. Okay. And now what do we do here? Okay, so I have 7x minus 1. Well, so is there a fast way to do this? What have we got here? So x can be, it is integers, right? Positive integers, so it's between 1 and 60. And obviously, if I put 1 in here, 7 times 1 is 7 minus 1 is 6. That's going to have a factor, well, it's going to have a factor in common with 6. So I need 7x minus 1 to at least be greater than 301. But I do still like that we did this 7x minus 1, because it changed, instead of having a whole bunch of different numerators, we just have one numerator. That's a pretty nifty trick, I'd say. So we definitely need that, so 7x greater than 302. 28, so 7x has got to be greater than 40-something. I'm not going to do what I did in the last question and waste our time here. So 302 divided by 7, 43. So it's got to be greater than 43. Greater than or equal to 40. No, greater than 43. Yeah, greater than 40. Because this guy here, 301, is 7 times 43. And maybe that's why they chose 301. So x has got to be greater than 443. So now we're looking at 44, 45. It's small enough, I think I could probably make a list. Although, as I'm writing this out, I realize I've got still like 8 more to go. I'm not liking my odds here. 58, 59, and 60. I don't like that it's all faded down there. I should have done a little better. I think we can rule out, if I do 7 times an odd number, so let's just clear the page here for a second. 7 times an odd number is odd, and then minus 1 is even. So we can actually rule out no odd numbers. So we'll only have 44, 46, 48. This is a much more manageable list. We could probably rule out the multiples of 3 really quickly too. 52, 54, 56, 58, and 60. And I'm just going to say, okay, this is my x. What's my 7x minus 1? And then I'm going to see, are any of these, they don't have to be prime, but they do have to be, well, they will be prime, because we're going to have 420, so 419 here. They're going to have to be prime just because their square root is less than this 301 guy here. So, just going to grab my calculator. So 308 minus 1, so 307 here. The next one will be 14 more than that, so 321. Then 14 more than that, so 335. So that one's out, because that's a multiple of 5. So this is a multiple of 3, this is a multiple of 5. Add 14, we're going to have 349. Then add another 14, we'll get something ending in a 3. Carry the 1. So 363, well, that's a multiple of 3. It looks like every third one will be a multiple of 3. That makes sense. 7, 3, 3, carry the 1. Just adding 14 each time because we're going up by 2's in our x's, and that changes to going up by 14's because we're doing 7x. So add a 4, carry 1, so that's an 8. Add on another 1, so that's 9. 391. And then add 4, add 1. And then adding 14 would get us this one as well. So not only is this a multiple of 3, but it's also a multiple of 5. Okay. So we have 307, 349, 377, 371, and 419 to deal with. Okay. I guess I can't think of. I mean, there's what, 6 of these? I think the easiest thing to do is just grab a calculator and see which of these are prime. So if you don't know how to test for a prime, let's just. I'll write out some instructions here. To test if n is prime, check to see if n is divisible by any prime p with p less than or equal to the square root of n. Now the reason this works is suppose n weren't prime, then it's composite, and I can write it as n is equal to a times b. Okay. But if these guys multiply to be equal to n, at least one of them has to be less than or equal to square root of n. Okay? So there will be a factor of n less than or equal to square root of n. I'm going to say it's a, it might be b, but if both of these were bigger than or equal to square root of n, then bigger than square root of n, then they'd have to multiply to something bigger than n. So one of them's got to be less than or equal to square root of n, and if a isn't prime, it's got a prime factor, and that's going to be even less. Okay, that's the reasoning behind this. So what did we have? Now I need to go back and copy my list. I know we had 419, so that was 60, and then I cannot remember the rest of my list. 391, 377, 349, 307. Uh, 391, 377, gosh, I cannot remember. So 391, 377, 349. That went with 50, 40, 54, and 56. $50, 54, and 56. Okay. So these are the ones I need to test, so I'm just going to grab my calculator. 307, what's the square root of that? 17. So let's see, 307, is that divisible by 17? It's not. Divisible by 13? It's not. Divisible by 11? Nope. Divisible by 7? Nope. And I would be able to tell if it's divisible by 2, 3, or 5. Okay, I've already done those visually. So I know 307 gets a little check mark. How about 349? Okay, so his square root is about 18.6, so I'm going to test all the primes less than 18. So 349 divided by 17? Nope. How about divided by 13? Nope. Divided by 11? No. And divided by 7, that should definitely be a no, because everything's of the form 7x minus 1. So 349, that's good to go as well. Okay, 377, that has a square root of 19. So 377 divided by 19? No. 377 divided by 17? No. Divided by 13? Oh, yes. 377 is 13 times 29. Okay. And I just realized we had 5 possibilities we've got here, and I think they had, yeah, between 1 and 5. Now we know at least 2 of them are fine, and not all of them are okay, so we've narrowed it down to 2, 3, or 4. So if I ran out of time at this instance, I would probably guess one of these 3. Okay, 391. What's the square root of 391? It's 19.7, so 391 divided by 19? No. 319 divided by 17? 23 times 17. Interesting, interesting, interesting. Okay, so now I know that it's either going to be 2 or 3 answers. So how about 419? Okay, so that it's about 20.4. So 419, are you divisible by 19? No. 419, how about divisible by 17? I'm going to guess that's a no, and it is. 13, that should be a no, just because they're so close to other multiples of 17 and 13 here. 419 divided by 11? Nope. And that's the last one I needed to check, because 7's not going to do anything, and we've already tested 2, 3, and 5 visually. So that one's good as well. So it turns out the answer was 3. There's 3 of them that work. 307, 349, 419. So X could be 44, 50, and 60. 3 possible values. Okay, so we have 3 possible values. That is C, our good friend C. And that finishes off the competition. Alright, so I am glad I brought my calculator, especially for 25. I know when I did the video for 24, I said, well, I'm going to do this without a calculator. But it really is advantageous, and sometimes they do make a question like this where you really wish you had your calculator. Yeah, not a whole lot to say. That wasn't a bad question. I feel like I stumbled upon that 7x minus 1. Maybe there's a better way to see it, or maybe there's a better way to do the question, frankly. Although, I think no matter how you do it, you're going to be messing with primes, and it's just going to come down to some calculator work at the end. Yeah, that's my only comment. So what's next? So we just did the Fryer, now we got the Cayley done. So the written grade 10 comp, the Galois 2004, that should be up next. And I'll get to recording and posting that. Thank you guys for watching. As always, if you want to, you can like or subscribe or whatever you want. But I'll see you guys for the next video for some more math.